Hi guys, in this video we are going to analyze the properties of liquids taking into account what we've been talking about in terms of intermolecular forces. So we're going to start off by discussing a couple properties of liquids that you no doubt have a fair degree of experience with. So the first one is this concept of viscosity. Okay, so strictly speaking, viscosity is a measure of a liquid's resistance to flow. So substances, liquids that have a high viscosity have a high resistance to flow. And we've got a couple examples here illustrated at the bottom of the slide here. So for example, honey, you have a very high resistance to flow. So we say that honey is a very viscous liquid. Okay? And this viscosity is the result of stronger intermolecular interactions. And this makes sense. If the molecules within that liquid are holding on to one another very tightly, they're not going to be as inclined to break apart and move around, which is required during the process of flowing. If the process of liquid flow requires the breaking of those bonds. Right? And so this viscosity is then essentially giving us a measure of the strength of those intermolecular interactions. The next thing I want to bring up here is the idea of surface tension. All right? So what we see is basically surface tension being the net attractive force towards the interior of the liquid that's experienced by molecules at the surface. Okay? And so to understand this, it makes sense if you think about what's happening at the surface of a liquid versus the interior of the liquid. And so to help us describe this, we're going to look at this little diagram that's basically zooming in on a water droplet. And you're looking at that water droplet from both the interior perspective on the bottom here and at the very side or edge of that water molecule. So as you can see, at the edge of that water molecule, the water molecules are going to experience strong attractive forces to all the other molecules inside. But on the outside, you have air, right? Air. And by definition of air, there's very little intermolecular interaction going on. And so as a result, the attractive forces are pulling inside towards the interior. And this results in this minimization of the surface area, which manifests as the beating of water. So whether you see dew droplets on a spider web here, as we've got illustrated on the slide, or water droplets coming out of your faucet, or water spilt on the table where you see it beating up, all of this is the result of this tendency of water molecules wanting to be close to other water molecules and basically minimizing the surface area that is exposed to the surrounding air. Okay, so our next example here, the next property that we want to discuss is this concept of capillary action. So capillary action is essentially refers to a rise of a liquid within a thin tube. Okay, and so we've got a little illustration here. We basically watch that liquid climbing up that tube. And this is something that you guys have perhaps seen if you say, put a little thin straw in your liquid at a restaurant when you're eating. You'll notice that the water in that straw will actually climb up a little bit higher than the water level in that liquid. And this occurs when the adhesive forces between the molecules on the surface of the capillary wall, whether it's a straw or glass, whatever it might be, and the molecules of the liquid are sufficiently large that that liquid wants to basically stick to the surface. Okay, and so that sticking to the surface results in basically that liquid climbing up. And it's this sort of process that is in fact actually facilitated by, for example, strong hydrogen bonding interactions, and it gives rise to the method by which water is moved throughout a tree. Okay, so it's this capillary action effect, water kind of moving up your straw here, that same sort of principle that actually gets the water moving up through the root system, up through the trunk and out all the branches and into the leaves of the tree where it's needed. Okay, because remember, a tree doesn't have a heart or vascular system as we do with mammals, right? It's relying upon this basic chemical concept. Okay, and looking at this capillary capillary action concept in action, actually shows us a very chemical level description of why this meniscus that we've been staring at in our laboratory activities all semester actually forms. Right? The meniscus is the result of the molecules in the liquid essentially trying to climb up or attach themselves to the wall of the container. Okay? Or the reason why wine, if you put it into a little cup, wine in a little cup, and you dip a piece of paper towel into it, the wine will end up climbing up the side of that container, climbing up the paper towel itself, right? Basically, you have water molecules and the OH groups on the paper towel surface because you've got cellulose fibers in there. That's carbohydrates, has a lot of alcohol groups on there, give rise to very strong hydrogen bonding interactions. And so that liquid, and you could do this with water or wine. Wine gives a very dramatic, coloration effect, right? Gives rise to a very prominent soaking up concept. So whether it's the little meniscus illustrated here, capillary action, in general, or liquid wicking up a paper towel, all of these are all instances of capillary action. The solution interacting with that medium that it's moving through. Okay, now something interesting can happen here, right? As I said, the formation of the meniscus that we're used to seeing, for example, here with water that has this concave look to it, is the result of strong forces, strong intermolecular interactions between that liquid and the container that's holding the liquid. But let's ask ourselves the question, what would happen if the intermolecular interactions between the liquid and the container are actually very weak? Well, that is in fact what happens if you consider mercury, which remember is actually a liquid at room temperature, mercury in a glass test tube, as illustrated right here on the right-hand side. Turns out that mercury does not interact with the glass very strongly. And this results in, like we saw before, that liquid trying to minimize its surface area, minimize its interaction with the container, and that gives rise to a convex meniscus. So you still have a meniscus, but now it's basically inverted. Okay, so the next property of liquids that we want to discuss here is actually something that we have a fair degree of background knowledge on, this concept of solubility. And so a quick recap here, solubility basically gives us a quantitative description for the extent to which a substance, which we call the solute, will dissolve in a solvent. Okay? And for our purposes, as we saw earlier in the course, typically our solvent's going to be water, right? But remember that solubility is a concept that we're going to apply to literally any solvent. And so in this chapter, we're actually going to start looking at some examples that are dealing with solvents that are not water, right? And these same definitions will hold. If there's a relatively large solubility, we say that compound is soluble. And so you could be soluble in water, soluble in hexane, soluble in whatever liquid you happen to pull out, right? And of course, substances with relatively low solubilities are said to be insoluble in that solvent, okay? And there's always a limit. Even if you have a soluble substance, that solution can only hold so much. And if you keep putting more and more solid in, at some point it will eventually fall out of solution, okay? And so one example that we saw earlier on in the class was this double displacement reaction where you take potassium iodide, lead nitrate, mix it together, and you get this insoluble lead iodide precipitate forming, okay? And so we can see from this reaction that this lead iodide product is in fact an insoluble compound. Now this example and other examples like this raise the question of why is it that certain compounds, certain ionic compounds in this case, are soluble, for example, the potassium iodide and lead nitrate, were perfectly happy floating around in solution, whereas other ionic compounds, like for example our lead iodine here, is not soluble. It will preferentially fall out of solution and bind with other lead and iodine ions. Okay? And well, of course, the answer comes down to the nature of the intermolecular interactions. Okay, so let's look at this. And so the basic idea here is, if you're wanting to predict whether or not a substance is going to mix up or dissolve in another substance, the first rule of thumb that we can follow is stated as follows. We basically say like dissolves like. If you're a compound that has charges, that has polar molecules, polar components, it has a net dipole moment, then you're going to be more likely to dissolve in polar solvents. Okay, so if you have a charge or a dipole moment, you're going to want to dissolve and hang out in solvents that have a dipole moment. Okay, similarly, if you are a solvent that does not have charges, does not have polarity, does not have hydrogen bonds or any of these factors, then you're going to tend to want to hang out in solvents that also don't have dipole moments, polarity, right, or high degree of polarity, or charges or hydrogen bonding. Okay, and so the in other words, polar molecules like polar solvents, non-polar molecules like non-polar solvents. Okay. And so to see why this happens, we can look at the right-hand side of the screen here, which we're basically illustrating the solvation process that happens when you put a sodium chloride or salt crystal in the water. And we all know that, from early on in our studies, that sodium chloride will readily break apart and dissociate and dissolve into water. And of course, you know this, if you put a spoonful of table salt into water, you can mix it up and you get salt water. Okay, so the reason for this phenomena is basically as follows. If you think of what happens when that chlorine ion breaks out of that crystal lattice and starts floating around in solution, or similarly a sodium ion breaks out, starts floating around in solution, what those ions end up doing is arranging the dipole moments in the surrounding water molecules, such that if it's a chlorine, you have positive ends, the hydrogen ends of the water molecules facing towards that chlorine. Okay, so the positive ends are getting closer to the negative ends. Okay, and so this is an example of a charge dipole interaction. Okay, a charge dipole interaction. And similarly, the sodium ions are going to arrange themselves so that the negatively charged, partial negative charge on the oxygen atoms are closer to those sodium ions. Again, charge dipole interactions, dipole moments just facing the opposite way. And so when you have the possibility of these strong charge dipole or dipole-dipole interactions occur, then you're going to be much more likely to have that solvent readily solvate whatever solute molecule you put in there. Okay, so this then brings us back to that question we posed before. What about these insoluble ionic compounds? Well, you have to remember that there's always a trade-off. In order to form these little solvation shells, which are of course energetically favorable, the price that you have to pay is the cost of putting in enough energy in order to break all the little interactions between the ions in this lattice. Okay, so you have to put in a fair amount of energy to break those ionic compounds apart. And remember, when we looked at the strength of different interactions, the charge-charge interactions in ionic compounds can be very significant. And so if the energetic cost of breaking those bonds isn't paid off in the formation of these solvation shells, then the compound simply isn't going to dissolve in solution, right? The ionic bonds are simply too strong. Okay, so let's go ahead and close out here with just a couple quick examples, looking at both these properties of liquids Specifically, I want to first look at this concept of surface tension, and I want you to consider a hypothetical scenario. Right, a hypothetical scenario involving a good old-fashioned belly flop. So if you look, let's say you have two different pools. One pool is full of benzene and the other is full of water. Okay, and I'm going to tell you that the viscosity of benzene is actually less than that of water. It's about a little less than 70% that of water. So water has a higher viscosity, right? I want you to now think of which would be more painful, a belly flop into a pool of water or a belly flop into a pool of benzene, okay? And of course, we're ignoring the obvious long-term negative health effects of swimming in a pool of benzene. Benzene is a known carcinogen. Again, by virtue of some pretty neat intermolecular interactions, benzene molecules can actually slide themselves into DNA strands. And so if you have a DNA molecule, right, a little bit of a side note here, right, a DNA molecule, that double helix here, you can have benzene molecules that basically wedge themselves in, something like that, and cause mutations. Okay, so we're ignoring that, right? We're going to assume that we're not going to get cancer from doing this. We're just looking at the pain involved in that initial instance of your stomach hitting this fluid. Go ahead and pause the video here and think about that for a second. We'll come back and answer it. Okay, so the answer to this question is actually going to be, the belly flop into the water is actually going to hurt worse. Okay, and the reason for this is because we're going to predict that the water has a higher surface tension. Right, it's going to take more energy to break apart the water molecules on the surface of the water, which is actually what's happening when you impact the water. You're having to break those molecules apart, and it takes a fair amount of energy in order to do that. Okay, and so the benzene molecules have a lower viscosity, which means they have weaker intermolecular interactions, which means the benzene would have a smaller surface tension, which means it doesn't require as much energy to break it apart. Therefore, easier to break apart, less pain when you flop in and hit that water. All right, so let's do one more example here. In this case, I'm going to present a variety of different compounds, and I want you to predict which one of these compounds would have basically be the best solvent for octane. Okay, so once again, I encourage you to pause the video here, look up what these compounds are, and come up with a prediction, and then go ahead and hit play, and we'll go through the solution together. Okay, so the first step here, and if you, especially for those of you that can't look at these names and immediately write out, have a little picture in your mind of what that molecule looks like, I encourage you guys to actually write out the structure of each and every one of these substances. So the first one up is octane. Octane is an 8-carbon hydrocarbon. 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. And of course, there's hydrogen atoms, associated with each one of these carbons. We've got a bunch of CH2 groups, so on and so forth. Okay. So the take-home message here is a long carbon chain. Water, we all know. Okay. Ethanol has an OH group on it. Right. A couple carbon atoms, ammonia, NH3. Benzene, remember, is this carbon, 6-membered carbon ring that has hydrogens kind of pointing out like this. It's this flat ring structure. Okay. All right. So basically, the game that we want to play here is we want to use this idea that like dissolves like. Okay. Like dissolves like. So we want to figure out which one of these compounds, A through D, is going to have the most similar intermolecular forces to this hydrocarbon octane. Okay, so right off the bat, we'll go through and we'll label the dominant intermolecular force. So in the case of our hydrocarbon, it's simply dispersion. Dispersion is going to be the dominant intermolecular force. And we can go ahead and put that, we can color code our intermolecular forces here. We'll put these guys in blue. Okay, so let's go through then and A through D and identify the strongest intermolecular force for each one. Water, of course, hydrogen bonding will be the strongest interaction. Similarly, the OH alcohol groups and ethanol, right, illustrated right here, right, are going to also give rise to the possibility of hydrogen bonding. You can also have hydrogen bonding in ammonia, okay? So A through C all have the possibility of hydrogen bonding. Now, if you go down to our last one here, benzene, there is no possibility for hydrogen bonding, and in fact, there's not even a possibility for dipole-dipole interactions, right? Because the relative difference in electronegativity between carbon and hydrogen is below that threshold of having a polar bond. So you've got a nonpolar substance, so dispersion is going to be our dominant force here. And so, of course, as you can see, dispersion is the dominant force for both octane and benzene. So following the dictate of like dissolves like, we are going to predict that benzene would be the best solvent of these options for octane. Okay, so that rounds out our overview discussion of different properties of liquids. What we're now going to do is take a closer look at the processes involved in a phase transition. Right? In other words, the movement between different states of matter, solid, liquids, and gases. And once again, we're going to rely on our understanding of intermolecular forces to do that.